Okay, so this is the lab number 2 for the mechanical 4259 computer aided engineering. And the two problems here, the first one is a ring that is hanging from a support with a pin, and the information is given here as well as the geometry. And uh, you're told that this bottom point, the bottom of the ring is pulled down by the amount 0.001 or zero point zero 0.01 inch, and you're supposed to model this thing, use the most appropriate elements, which is going to be a beam problem. You have to use beam problems here, okay, and or beam elements, and use symmetry as much as possible. So as far as the beam element, we know what to do. Uh, but as far as symmetry, you look at this problem, it becomes obvious that the behavior on the right side and the left side are identical. So all you need to do is to model half of this. Okay. Now I made some comments in the lab about the fact that because of the geometry and the loading and the restraint, this pin essentially becomes a clamp, although it's not drawn like that. But you can see why, because there's nothing that makes this thing wobbles to the right or to the left, and there is no force that is making it rotate perpendicular to that axis. Okay. Uh, and nothing that obviously makes it rotate about the third direction. No force that causes it to rotate about that third direction. This being the case, three translation being zero here and three rotations being zero here essentially makes that thing a clamp. Now, some of you in the lab may have done that, just clamped this thing, and it went with no issues. But the people who actually did not clamp this, they ended up adding a lot of other constraints to make it work. And this is fine. There's nothing wrong with it. So what I'm going to do is basically do the problem both ways. First, clamp it, and then of course you have restraints here for symmetry restraints here, and then pull it down. And then once I do that, I'm going to go back and start putting a pin here, and you see that as you run it, it bombs out several times until you fix it. Okay, so first I'm going to clamp it here, although that is not what is shown. So let's go ahead here and create this geometry. Let's see now, on that plane I'm going to sketch a circle of diameter of radius 10. That's what the radius that uh, loop is. So let me draw a circle here. Now we have two choices. We can draw the circle and cut it, or we can do only half of the circle, and that's exactly what I'm going to do. So let me escape this. Instead, I'm going to do a center circle, an arc basically. So uh, I'm going to do it like this. Because even if I had done a circle, I would have had to divide it into two because of the symmetry. So here is the dimension. This radius is going to be 10. Obviously, we're going to have to fit this. Okay, good. Uh, yep, exit. This is all we have as our model. Let's apply material to it. By the way, do not forget to join. If you don't join this thing, because it's in a sketch, you won't be able to mesh it. Okay, so first let me apply material to it. Now the material, you're given specific values for Young's modulus and Poisson ratio. If I put steel here, or in fact any material, double click on this thing, notice that the Young's modulus of the steel and the Poisson ratio that is in the database is slightly different from what I'm given to you. So, I mean, if you want to exactly the way I've described it, you can make this thing 3 and Poisson ratio 0.6, sorry, zero point 0.3. I did not expect you to do that, and on the test, you should know how to change it, but I'll try to say use default properties, etc., unless you're specifically asked to change it. Okay, good. So I changed that, Now we have to go and join this thing. Now remember, join cannot be done here. This is part design. To do the join, what I showed you is that you go to shape, generative shape design, and this is where you find the join icon. And must be somewhere here. Let me see. Is it hiding back there? No. My join is hiding. So let me remind you how you reset your toolbar so that you can see them. It's in a toolbar called Operations, and I can get it here. However, I'll remind you how to reset the stuff. So you go to Tools, Tools, Customize, Customize. You just wait for this thing to pop up. The first time that you do this thing, it takes a few seconds. Okay, so you say Toolbars, Restore all contents. Okay, and restore all positions. So this basically put them to the default position, and I don't need this, or I don't need that, and I bet if I drag these things out, I can find the uh, toolbar reset operations where the join is actually located. Right there, I can see that, right there. This is called operations, make it like that, so you can see it, operations, and there's the join, okay? So there we are. You select the sketch. Without doing this thing, you will not be able to mesh this part later on. Okay, so let's go ahead and to uh, analysis and simulation. Okay, we are doing a static analysis. Good, and we're going to measure it. Beam measure. Without joining, you will not be able to do this. And I'll use this default value for the mesh size. A lot of elements unnecessary. Now, because the cross section is circular, you really don't need an orientation point. You actually don't need it. So you go to the 1D property here. 1D property, you make sure that the cross section is not a rectangle, it's a cylindrical beam. And you click on the wrench, you put the radius, which is 1. Radius is 1, diameter 2. That's what you were told the problem. And notice that you can actually, oh, yeah, the support is there. There's the support. And this is basically 2-inch diameter circle. And you can close it without selecting the orientation. Okay? So we say, all right. Now, let us go ahead and clamp the top. Now remember, clamping is going to save you some hassle. But some of the people who actually followed the instructions that was given on the assignment sheet did not clamp, and I had to go and help them. Okay, there's a clamp. Okay, now this is in the plane of symmetry, so you click on the user defined restraint, and let's watch what coordinates, what the plane of symmetry is here. XZ is a plane of symmetry. As soon as you say this point is in the XZ plane of symmetry, it does not move in Y, does not translate in Y, and rotations are exactly the opposite. Do not forget to activate the rotations, okay? And the support, of course, is this vertex, okay? Good. And we say, okay. Now, this is for symmetry. So let me go ahead here, and just so that I don't mix these up, I'm going to rename this thing. Let me actually double click on it and call it, this is for symmetry. Because I also have to make it a 0 displacement in the downward direction because we want to change it later on to 0.01. I don't want to mix these up. This is going to confuse you, and this is for symmetry, okay? Now, we also want another user-defined restraint, only displacement in the direction Z, only displacement downward, direction Z, for that same point, okay? And this is the one for pushing down, If you put these things all in the same dialog box as symmetry and this together, it can be done, but it's a bad idea. It's going to confuse you. Sure it will. Okay, so this is for pushing down, and now we can go and change this thing. You're going to select this restraint. Notice that we are not selecting the point, you're selecting the restraint, pushing down, and the amount is negative 0.01. Say okay, and we run it. Let's look at the view from the front. Okay, first thing, you can look at the deformation. There we are, and you can animate it. Notice that symmetry will not allow this thing to go to the left or to the right. It just goes straight down. And if you want numbers, displacement values, let me double click on this thing, take average ISO, and you can see that the maximum deflection is 0.01, which I impose downward. Now, uh, you're also asked to find the force. So the way to do the force, you go right click down here, create resultant sensor, reaction sensor, and it's going to ask you what restraint do you want to use in order to find the reaction value force. So I can use the top one, or I can use this pushing down the strain, either one. And don't forget to update 751. And remember, this force is the amount of force needed to displace this half the ring. Okay, so if the question was how much force is needed to pull the bottom of this ring down by 0.01, the answer is going to be double of that. Okay, this is only for half of the thing that we have modeled. The actual force needed to pull that ring down by 0.01 is double of that, right, to 1,500 pounds. Okay, good. So let's go ahead, close this, and do not forget to say okay. Don't cancel it, because on the test, if you say cancel, even though you may have written the correct answer, we don't know where you got it from. But if you say okay, so that it's reflected in your reaction, I can always go and double check on this and so find out where you got your number from. Okay, good. So let's close this. Let's close this. I don't want that. Now, let's go back here and get back into the analysis. This time I'm not going to clamp the top, okay? So let's go ahead and do another analysis, generative structure analysis. We have to go through these initial steps again. So we mesh it right there, same mesh size, okay, no problem. And then we're going to put the properties, cross-sectional property here, 1D property. The support is right here. It is cylindrical. The radius is correct because we just did it a minute ago. And we can close this. And now the top, I'm not going to clamp, because this drawing doesn't show you anything about clamping. It shows you a pin. Okay, so let's go ahead. First of all, do the following. These 2 points, lie in the plane of symmetry x, z. We just discussed that. So let's go ahead and apply symmetry constraint. So user define. Let me uncheck all of these. Let me call this thing symmetry xz plane. Now, as soon as you say symmetry xz plane, this point and that point, the two points, as soon as you say that, there is no displacement in y and rotation exactly opposite. We just discussed this a couple of minutes ago. We say, okay, good. Now, here is my restraint that, and I gave that name. Okay, let me hide this thing so that you can see it good. Now, this point, because of that drawing, is also pinned, does not go in the direction x, z, and y. Now, y won't go anyway because of the symmetry. So we can say x and z are fixed. So let's go ahead here. So another one, I'll say pin condition. Already we know that it doesn't move in the direction y. We already know that. But if it's bothering you, you can always say x, y, z. However, there is no need, because x and z is all we have to do. That point, this particular point, just x and z. Okay? It doesn't move in direction y because of symmetry. Good. Very good. And this point is going to be pushed down, is it not? This point is going to get pushed down. Okay, so let's see now. Also, another one. Let me uncheck all of these, and I say push down, bottom point. How about that? Bottom point. There's no O here. Push down, bottom point, and we select this point. Okay, in the direction Z, because you want to change that. You want to say its value is 0.01 later on. So we say okay. And now we can go do an enforced displacement here for this restraint, and we give it negative 0.01. Now, let's run this thing and see what happens. Okay, so if it still bombs out, we have to go and do a few more things. I think it's going to be okay. Oh, it does. Now let's find out what happened. So let's go ahead and look at the deformation and animate it so that we can see what's going on. So let's see. If you look at the view from the side, notice that this whole thing can actually rotate about this top point. That's because we already said rotation about, let's see now, let me cancel this thing. Let's go back to that initial, this restraint, symmetry restraint. So we already fixed rotation about X and Z, but it can rotate about Y. So I'm going to do one more constraint on that top point, for example. Uh, on that top point, we also fix rotation about Y. Okay. Let me give this thing a name. Rotation about Y. So when you think about it, if we do this, all 6 components way up there have been fixed. Okay, that's why it became a clamp essentially. So this is top point, rotation about Y being fixed. There, about reduction 2. Let's run it. Done. Okay, so if you look at the deflection, 0.01 as we expect. If you look at the sensor, right click, not there, right click, reaction sensor, uh, reaction sensor. Okay, so let's see now. We can take, for example, that push down and update, and you get your 700, roughly 750. Look, so all I'm saying is that this last thing prevented that freedom that it has to rotate about Y. And as soon as you did this, all 6 degrees of freedom up there were fixed, and therefore it became a clamp essentially. So that takes care of this problem 2 different ways. Either way, you would have got full mark, except that for people who clamped it and they got away with it, we give him the benefit of the doubt that although it was not said that it's clamped, but maybe they knew what they were doing. Okay, either way, it's good. Remember, the force needed to make that deformation is double of what is in the sensor here because of the fact that we are modeling only half of the strip. Okay, so now let's do the other problem. Let me see now. This one is good. Let me close all of these. And close this. So where's my other problem? This problem now for the yeah. is problem 2. It says use symmetry to reduce the model as much as possible. Use the most appropriate elements. So you look at this, you have to realize that this must be done with beam elements. Do not do it with solid elements. Okay, and these ends are clamped. This middle point is pushed down by some amount, and you have to realize that the XZ is a planar symmetry. So I need to model only half of this. Okay, and yeah, and we move on with the rest of the problem. So there's some dimensions given here. So let me see now. This is 3, and yeah, this is 3, and this is also 3. Okay, so let's go ahead and create our model. We have two choices. You can do it in a sketch, or you can do it in as a wireframe. That's entirely up to you. So I will do it as a sketch because it's easier. I'll model only half of it. So on that vertical plane, I will sketch something that looks like that L. So something like this perhaps. And we'll give it dimensions in a second. Okay. So let's see now. Dimensions. This is going to be 3, 3. Again, this is going to be 3. And this is going to be 6 inches. Yep. Okay, so there's my geometry. I exit because the cross section is a circle. I don't know what is the radius. 0.25 diameter is 0.25 inches. I don't need an orientation point, so this is fine. Yeah, let's apply material to it. Can't remember what was the steel. It says steel, right? Steel with default properties. Okay, good. So let's go ahead and apply material to this. Metal and steel on that part. We say okay, and do not forget to join. Now I just happen to be in generative shape design, so the join is here. If you were in part design and you did this thing in part design, you would have to switch to generative shape design to find join. Join, you cannot find it in part design. You click on it, you select that sketch, and it joins it. Okay, and now we're going to go to generative structure analysis. We're going to mesh this. Okay, I'll use the same default element size, whatever I had in the last analysis. And then we're going to do the 1D property. Make sure it's cylindrical, and make sure you click on the range, is the correct radius. Now the radius is 0.125 because the diameter, I believe the diameter was 0.25, so this is going to be 0.125. Okay, and of course the support is right here, and you can see that it put tiny little circle here, and same thing up there, etc. Good. So now this point is clamped. We're told that this point is clamped. All right, and this point obviously is in a plane of symmetry. So let me select this point. And since I don't want to mix up the issue of planar symmetry with pushing down, so I say symmetry, this is a symmetry restraint. It lies in the XZ plane, so it does not translate in direction Y, direction 2, and rotations are exactly the opposite. In other words, because this is fixed, rotation is free. Because these are free, these translations are free, rotations are free. That's the way it works for symmetry. Okay, you may want to think about this and see whether it makes sense or not. Okay. It does make sense. Okay, so let me hide that symmetry restraint because I want to be able to pick this point easily. So do another one which says pushing down. We call this thing pushing down. Pushing down. Okay, so to push down, first we have to push it down by the amount 0. That sounds ridiculous, but that's the way it works in CATIA. And now we can go change it. So you go to enforce displacement, you select this and you say negative 0.01. Okay, and this is pretty much it. I'm pretty sure it says zero point zero 0.01, right? Yeah, 0.01. Point 0.001, sorry. Okay, no problem. So double click on this, put an extra 0 here. Okay, good. We're going to run it. Yeah, so a deflection like that, if you look at the view from the front, there we are. If you want actual numbers, you click on displacement, and if you want color, colorful contour plot, like that. Obviously, I pushed it down by 0.001. I don't expect anything to get here, anything else to get here. As far as the load that is needed to do this, because notice that these are coming from other, tests and things like that. At that point, these were the part marks that were given. Be aware of the fact that this is the way it was several years ago. Okay, your scheme, your marking scheme may be different here, and you have to write down the magnitude of the force needed to create this displacement. You're gonna be asked to write down a number in this box. So what you do is you go and create your sensor. Right click, create a sensor, reaction sensor, and it says which reaction is it. You can select this top, the clamp, or you can select the restraint that you use to push down. Okay, and then update, and you get almost minus 1 pound. Okay, now remember, this is so low. That's because think about it, the diameter of this steel kind of hanger is I don't know, was 0.25, right? 0.25 is not a lot of diameter, so this is a very small amount. Now, the number that goes in this box is not this number, but it's the double of this number, okay? Because you're modeling only half of the structure now in this particular problem. Now, make sure that you say okay so that we have listening recording in your tree, so that if you want to know where you got this number that you wrote down on your exam paper, we go to your tree, we better be able to find it there. Because otherwise, we're saying that you just guessed it, and that's not acceptable. Okay? Double of this goes in that box. Okay, that takes care of both problems. Good luck.